So, good evening, everyone. My name is Mohit, and on behalf of the Helsinki-Aalto Institute for Cybersecurity, I welcome you to the last formal event of our demo day. And I really mean it when I say it that we have saved the best for the last. So, we will now have a hike talk by Dr. Elissa Redmiles. I'm sure after this day you are familiar with HAIC and that we have a public outreach program where we invite experts in the information security field to give enlightening talks. And today's talk is going to be about learning from people. So I would like to introduce our speaker for this evening. At least it's evening in Helsinki, even though it's morning where Dr. Elissa Redmiles is based. Uh, she has received a bachelor's cum laude, master's, and a doctoral degree in computer science from University of Maryland. She's a faculty member and research group leader at the Digital Harm Group at the Max Planck Institute of Software System. And she additionally is a consultant and researcher for multiple organizations, including Microsoft and Facebook. So she is really extraordinary that she doesn't work for one of the top employers in the world, but two of them. Uh, she uses computational and economic and social science methods to understand users' security and privacy and online safety related decision making processes. Her work has been covered in Scientific American, in Wired, Business Insider, Newsweek, Snare on Security, CNET, you name it. She's also been recognized by multiple distinguished paper awards at Usenix Security, as well as the John Carrot Usable Privacy and Security Research Award. So I think on the Facebook advertisement that we had sent, that anyone else at her stage would be called a rising star, since she's recently finished her PhD degree. But she is already a star, and we are really honored to have her as a guest for the Hack Talk on this demo day. Um, Please go ahead. I think Nina, if you can share the controls.
Awesome. Thank you for the very kind introduction. Let me get my slides up here. Okay, are you able to see the slides?
Yes. Yes.
Okay, wonderful. Yeah, so today I'd like to talk about how we make decisions. And so we have to make many decisions every day in our lives. And we have kind of two ways to make them, right? We can either take our own sort of expert viewpoint on what we should do, or we can look at those around us and sort of infer from what they're doing how we should proceed. And in computational problems, we also have to make constant decisions, right? So we might have to decide, what features are fair to use in a machine learning classifier, or what security requirements we want to set for end users in a particular technology platform. And typically it's experts who set best practices and make these decisions. When experts are making these decisions, they're making trade-offs. And so this figure is from a case study where a set of researchers looked at sort of they reflected on their own decision-making about whether to release some research data sets. And they realized that they were trading off sort of the benefit to science from releasing those data sets against the risk to the people in the data sets that they might be identified. And so this is similar, right? When we think about machine learning, we might be trading off improvements in classifier accuracy by having certain features in a classifier against like the unfairness of maybe including some feature that someone doesn't have control over, or which is linked to them being a member of a sensitive group. And for security, we might be trying to trade off the burden to an end user from having to do a particular security behavior against the benefit to their account security. And one of the problems with experts making these decisions is that experts don't always agree, right? There's lots of examples we can look at in the past where experts, turned out to be wrong. And that's okay. We, correct our advice, or sometimes we disagree, and that helps us improve. But perhaps more critically, users and experts may disagree. So the way that experts think we should trade off between, say, benefit to security and burden to end users might be quite different from how users would trade off, not just because experts might put different valuation on security versus burden, but also because experts may not fully understand the magnitude of burden, say, for particular groups of users. And so this tension between sort of experts' trade-offs or experts' ways of setting norms and making decisions versus what users want to do is a classic tension in moral philosophy. So long before the internet happened, moral philosophers were discussing this tension in terms of making laws and rules for societies. And they basically describe that there are these two ways to make these rules or decisions. The first is normative, where experts sort of prescribe best practices. And the second is descriptive, where experts learn from non-experts' preferences and behavior and then infer best practice. And it's not necessarily the case that we have to pick one or the other. We can also try to pick a point in the middle. And so in this talk, we're going to explore the question of whether we can use descriptive approaches, so learning from users, to help us make better computational decisions. And when I say better, I mean more aligned with users' values, and in some ways more ethically robust, and also things that make decisions for technology in a way that will encourage users to actually adopt that technology. And so we're going to explore 3 different case studies with 3 different levels of descriptive methods as different examples of how descriptive approaches can help us solve problems in computer science. So the first is we're going to talk about how we can use observations of user behavior to help us better set security policies. In the second case study, we're going to discuss how we can use asking people about preferences to determine what features to use in machine learning algorithms. And finally, we're going to take sort of an extreme example of descriptive methods where we directly make decisions and rules together with users when trying to establish guidelines for the content that should be allowed in virtual reality. So we're going to start by talking about security. So generally, security researchers and particularly security professionals have this goal of getting users to behave securely. And one of the ways that we do that, right, is with that we prompt users to do different security behaviors. So many of you have probably seen a screen that looks like this one, where a tech company is trying to prompt you to protect your account with 2-factor authentication or 2-step verification. And so one of the questions that's often raised is how do we get people to actually, click yes and protect their accounts when they see these prompts? And so the normative approach is to just kind of prompt everyone all the time until they do the behavior. But today we want to explore a descriptive approach. And so in that approach, we're going to model how users respond to prompts and then try to optimize the prompts based on their natural behavior. So we're going to try to adjust those prompts to kind of fit in with how users naturally behave. Okay, so why don't people behave as expected or as we want them to when prompted? There's this famous quote that the user is going to pick dancing pigs over security every time. So basically users don't care about security or just sort of picking randomly and they're focused on something else. And in fact, a couple of years ago, there was a plugin for Instagram that would generate pictures of dancing animals, but you had to hand over your account credentials. And this was a phishing application. And so people were literally picking dancing pigs over security. And so we want to make sure, though, that that's actually correct. Like, are people just making random choices, or is there something kind of more well-reasoned going on? And so in order to answer that question, we want to try to model how people respond to 2-factor authentication prompts. And in order to do that, we're actually going to use like a behavioral economics style set of experiments, and I'll explain those in a minute. So in general, when we want to try to model end user security behavior, we have a couple of choices, right? We can say, okay, let's partner with a tech company. Let's look at their data of what people do when they're shown a prompt, and let's model that. that's great because we have high, ecological validity. It's really representative of the real world. But there's a bunch of different confounds that we can't really control, right? So maybe everyone doesn't value that account the same way, or people have different skills that are hard to measure in this kind of in the wild setting. So doing things in the wild can be really useful, but sometimes we want to be able to do controlled experiments. And so that's why we're going to do these kinds of controlled experiments I'm going to describe, so we can very carefully model how people respond to prompts. So in order to do that, we built an online experimentation system where people can create a simple bank account. And that bank account is going to hold their compensation for the study. So we're going to pay them from taking part in the study, and that compensation is going to be in the bank account. And this account has an explicit risk of being hacked. And being hacked means that people don't get paid any money. And it's done by a random number generator, so we're not letting attackers try to get into these accounts. But the key is that this risk is explicit. So we're actually going to tell people how much risk they have of being hacked and see how their behavior changes. People are going to have the option to make a security choice, so they can enable or not enable two-factor authentication. If they enable two-factor, it will lower the risk of hacking, and they're going to be told how much it's going to reduce that risk. But of course, just like in the real world, it's going to increase their costs to complete the study. And one of the nice things that we're able to do is, because this is a controlled experimentation system, we can control very carefully how long, say, it takes them to get the two-factor code, whether it's the right one the first time, etc. And finally, we're going to use a very particular set of participants. So people are going to stand to lose money or to not get paid for their participation. And we're going to use participants who earn money from small time increments. So we're going to use crowd workers. So these are people who, either as their full-time or part-time job, they go on crowd work platforms where they perform like tiny tasks like taking surveys or labeling images for machine learning for small amounts of money. And the nice thing about these participants is they are really cognizant of the value of their time. And so when we have two-factor authentication that takes up, say, 30 seconds, for them, 30 seconds is actually a meaningful amount of time, whereas for you or me, it would be sort of hard to reason about what a 30-second loss means. Okay, so to give a little bit more detail, when crowd workers join the experiment, they create a bank account where they enter their mTurk ID and they create a password. After that, they learn the risk of being hacked. So we describe the study. We say, at the end of the study, you'll be compensated with the amount of money left in your bank account. You'll begin the study with $5 in your account. $5 is the average hourly wage for these crowd workers. We also tried variants where we use $10, etc. You must log in once a day. Otherwise, you'll lose all of the money in your account. And the reason we want them to log in once a day is if they choose to enable two-factor authentication, we want to make sure they have sufficient costs from using it. If you're hacked, you'll lose all the money in your account. And then they're told the risks. Studies indicate that 20% of users will have their study accounts hacked. As I mentioned, we tried different variants with the dollar amounts. And in addition to trying like higher and lower dollar amounts, we also explore sort of a traditional economic effect, which is called the endowment effect. And in the endowment effect, economics research has found, at least in offline behavior, that people care more about protecting what they already have than what they're earning. And so in this variant of the study, people begin with $1, and every day that they log in, they earn an additional $1 up to $5. So they still end up with the same amount, but they're earning it over time instead of starting with it at the beginning. We also vary the risk of hacking for different users so that we can start to try to model their behavior in response to these prompts. Then users are offered the option to enable two-factor authentication. We used phone-based two-factor not because it's the most secure, it's not, but because it's the easiest to control. And it's also, mTurk crowd workers are used to giving out their phone number for studies. So there weren't particular privacy concerns. This particular participant was told that two-factor would protect them from hacking 90% of the time. So their 20% risk of hacking was reduced to 2%. And we had some questions checking their understanding of that math. We varied this risk of hacking again, this protection from hacking. And then if they choose to do two-factor authentication, they get a traditional SMS-based two-factor. They have to enter the code, and they have to do this every time they log in. And they have to log in regularly, as I mentioned before. Okay, so only 52% of participants enabled two-factor in this experiment. And in fact, this is higher than what you would see, out in the real world. So, Google has reported two-factor authentication rates below like 10%. Some more security-oriented places have reported rates like 60 or 50%. So this is a little higher than normal, maybe because we're getting like explicit risk, but it's not as high as, security experts wish that it was. And so now we'd like to understand, why. We wanted to see, is there a consistent pattern in security behavior? Can we actually build a model that explains people's behavior, or do we have to kind of go back to the dancing pigs explanation and people are doing things randomly? So we're going to predict whether or not people enabled two-factor as a function of the account value, which is either like $5 or $10, or endowment versus earning. We're going to include the risk factors, so the chance your account would be hacked and how much protection was offered by two-factor. And then we're going to have a series of controls. So recall that at the beginning of the system, we asked people to create a password. When we do that, that password didn't have any effect on the risks in the study, but it's possible that people may have thought that by making a stronger password, they were more secure. So we controlled for their password strength, measured using an existing tool. We also controlled for internet and security skill, which we measured using some pre-validated sociological scales. And we also controlled for demographics. None of those controls were significant in the models, but people's behavior was significantly related to account value and the risk factors. Next, we wanted to add in some additional factors. So the first was costs. So beyond just like account value and risk, which explain about 16% of the variance in people's behavior, let's see if there's kind of some other things that would help explain more. So if we take a look at costs, what we see is that different participants had very different total times to log in with two-factor authentication. And actually these login times are correlated with their internet skill. So users who have stronger skills were able to log in faster, users with weaker skills were logged in slower. And so we ran our experiment a couple of times so that we could actually look at people's costs and use those in our model. We also used their past behavior. So in subsequent rounds of the experiment, we used what they did in the first round. When doing first round models, we used their self-reports about what they typically do. And then we also have the controls, which were still not significant even in this larger model. And what we see is that if we just used risk and account value in the model, we'd be able to explain about 9% of people's behavior variance. And as context, when psychologists build models of, say, like consumer behavior, so what you buy at the grocery store, et cetera, they're able to explain like 30 to 40% of the variance in that behavior. So we're doing okay with just risk and account value, but there's definitely more to the story. Once we add people's costs, so like how long it's going to take them to do two-factor, we're able to get quite close to kind of one of these good psychology models. But once we add their past behavior, we're able to explain 61% of the behavior variance by having this like 4-feature model. And what that tells us is that users aren't just sort of paying attention to dancing pigs or flipping coins to make decisions. They're actually making reasoned decisions about whether or not to enable at least two-factor authentication. They're affected by some, kind of cognitive biases. So this, the fact that they really want to hang on to their past behavior is something called anchoring, and that's seen in a lot of other behaviors where people just really want to stick with what they've been doing. And also when we look at kind of that endowment, like whether they're earning the money over time or whether they started with it, that's another kind of cognitive bias, right? Because, if I earn money in my bank account from my salary, I should be protecting it for the future value, not for today's value, but that's not quite how humans work. But in terms of like costs and risks, it's totally reasonable for people to try to make those trade-offs. Now, of course, if we take these models out to the real world, we would expect to be able to explain a significant percent of behavior variance, but not as much as 61%, because it's very hard for us to characterize for users, what is the risk of this account being hacked, or it may be hard for them to reason about account value in cases like Facebook accounts or email accounts where it's not sort of a dollar quantity. So in summary, people's security behavior, and we've seen this in other studies as well, it is explainable, it's not random. And differences in ability and in people's valuation of their account, where ability kind of influences costs, can alter behavior as well as sort of what people typically do. And so these are, the fact that like differences among people can alter behavior is something that we want to be able to accommodate. And so when we do normative solutions where we prompt everyone to use two-factor until they do, we have a couple of problems, right? People are so inundated, they start ignoring the prompts. We've seen this a lot in security. And also it's sort of unfair because not everyone is getting the same value out of the same behavior. So, right, people are not all at different places. They have inequities in their ability of doing two-factor, inequities in the value of their account. And so getting them to do two-factor kind of has different value or costs for different people. And so in taking a descriptive approach, we want to take our learnings from user behavior, so take these models, to be able to actually adjust how we prompt people. Like, do we prompt them to do two-factor? Do we prompt them to do something else? When do we prompt them? Do we prompt them after their account has gained value? So maybe a month after they've been using it instead of immediately, et cetera. And also think about distributing resources. So Google, for example, hands out YubiKeys to high-risk users because those are easier sometimes for people to use than two-factor authentication. So like, how do we customize like the messages and the resources people get so that we can kind of balance things out and that everyone is putting in approximately the same effort for the same benefit. In order to do that, we're going to use a technique called mechanism design. And so mechanism design comes out of game theory, and it's a way of sort of reasoning about a system and then figuring out how to optimize it. And so if we think about like a tech company, so let's say Facebook, they have a set of different kind of values or factors that they control. So they control what behaviors they offer to users. So is it two-factor authentication? Is it alerts about suspicious logins? Is it YubiKeys? Whatever it is, they control that. And they, to some degree can pick between, say, different two-factor providers where one might be, more protective, like an app-based two-factor, but it might be a little more cumbersome for people to use than SMS. They also choose like what prompts they give to users and when they choose to prompt them. And finally, they can control whether they allocate extra resources like YubiKeys or like a helpline for getting people to set up. And if we now have this model of users' behavior that's based on, factors of the user, so their skill, their account value, past behavior, if we can kind of use the models that we've built, then we can predict based on, a particular set of behavioral offerings, a particular timing of prompts, whether or not we allocate resources, et cetera, how are my users going to behave? And that can inform companies' cost models, right? So they have a cost model for, if some subset of these users get hacked, how much is that going to cost me? Okay, and if I know, whether or not they're predicted to do, to adopt certain behaviors, now I can predict, how likely is it they get hacked, and now I have some costs. And I also have some costs from offering different behaviors or offering YubiKeys, et cetera. And all of this can kind of feed into my profit model. And of course, the users feed into my profit model as well, right? I want to keep them engaged. I want to keep them clicking on ads, so on and so forth. So I kind of need to balance the costs from them potentially getting hacked if they don't do security behaviors against the reduction in profit if I lose engagement. And so in these systems, we can then start to optimize. So we can write sort of a math equation that says, let's please maximize profit And we can make adjustments to these factors within, some budgetary constraints and some real world constraints where we can't get like perfect security behaviors. And given a user behavior model, like how do we decide what's best for different groups of users? So we can actually individualize this optimization per user. And so what that allows us to do is not only to personalize things, right? But also to make things a little bit more equal. So again, if I can allocate resources to people, then I can start to add constraints. And I can say, well, I want you to maximize profit, but I also want you to minimize the difference in the amount of time or cost it takes different users in my platform to do security. Or you could say, I want to make sure everyone has approximately equal risk of being hacked to make it more fair. So we can start to introduce these kind of ideas of fairness, as well as sort of optimizing profits and sort of prompting people in a way that feels more natural to them. Okay, so basically, we observed people's behavior in a controlled environment. We inferred their preferences, things around account value and ability based on our models of their behavior. And then we can use those models as inputs to the decisions that we're going to make through that sort of optimization type system. And so, one question you might ask is, could we get to the decision sooner? Like, could we just ask people, what they want? Now, in the case of security, that may not work very well because asking a user, do you want two-factor authentication? Do you want login alerts or do you want a YubiKey? They may not have the appropriate knowledge to answer those kind of questions. So we may need to kind of observe them in the laboratory and infer from their behavior what they need. But in some other settings, we can more easily just directly ask the users what they'd like. And so in this next example, we're going to talk about trying to determine which features are fair to use in a machine learning classifier. And so we're going to try to model how people reason about fairness. And then we're going to think about how we could like weight the features that we use in the classifier based on people's preferences. So, one question you might be asking is like, why do we even care about what features go in the classifier, right? Maybe people don't care about that. They just care about whether the classifier is accurate. So a number of years ago, there was an issue where Google's algorithm for advertisements showed prestigious job advertisements to men, but not to women. And this caused a major amount of concern from the public and from technologists. And so in some prior work, we looked at, why were people so upset and what drove their concern in this advertising discrimination scenario. And in order to ask that question, we conducted a series of surveys. And in these surveys, we gave people scenarios that sort of matched what had happened in this advertising discrimination. And so what we said was, okay, imagine there's a firm called Systeme, and Systeme is a local tech firm that develops software. They're expanding and they want to hire new employees. And they contract with Bezo, an online advertising network, which places their job ad on a local news site. And then we said an HR employee at the tech company chooses to target individuals who are Asian rather than individuals who are white with this ad. And as a result, the ad is shown more frequently to those who are Asian than those who are white. And we tested out different sort of explanations for the same result, which is the ad being shown more to individuals who are Asian than individuals who are white. It could be that the tech company requested that this ad be shown to people who had recently visited technology-related websites. And people who are Asian tend to do so, and therefore the ad was shown more frequently to those who are Asian. It could be that the advertising network charges less to reach individuals who are Asian than individuals who are white. And so the marketing computer program for the tech company just automatically selected the less expensive option, but it still resulted in this discriminatory outcome. Or it could be that those who are Asian tend to click on different ads, so on and so forth. And so we wanted to try to figure out, do these kind of different scenarios matter? And also, does it matter if we change who benefits in the discrimination? And in order to do this, we built some regression models where we did cross-validation on a census representative panel. And so a census representative panel just means that we surveyed people whose demographics matched those of the population we're trying to reason about, in this case, people in the US. And what we find is that features are a key factor in people's fairness perception of the scenario. So depending on whether the advertising decision was made based on someone explicitly targeting a demographic versus some group demographic tending to behave in such a way that they got targeted, so clicking on ads more, et cetera, people had very different perceptions of the fairness. So when it was explicitly a demographic, far more people found it to be like a moderate or serious problem than when it was just behaviorally based. The other thing we find is that who's doing the targeting doesn't matter. So whether it's an HR employee or an algorithm, nobody cares. Totally almost identical. And finally, majority groups. So in a racial scenario, those who are white perceive any minority group benefiting as less problematic. But minority groups, whether or not they're the group that would benefit, find the scenarios problematic overall. And so the thing that is sort of key for us today is this idea of features mattering. And this came up again a couple of years later. So in 2014, ProPublica kind of broke a story that judges in the United States were using an algorithm to determine whether or not people should be released on bail. And so this company had started providing this algorithm that predicted someone's recidivism risk, their chance of committing a crime again. And they predicted it as high, medium, or low, and judges were using that in their decision about whether people could be released prior to trial. And in order to predict this recidivism risk, they were using people's answers to a questionnaire. And this questionnaire included information about current criminal charge, the criminal history of their family and friends, their performance in grade school, their mental health status. So unlike the last scenario where it was like gender-based in the real world, and in our scenarios, we tried a bunch of different things, it was nothing legally sensitive or banned. But there was still a lot of controversy about them using these pieces of information. And so the answers to this questionnaire turned into surveys, turned into features, which were used in the classifier to predict, right, this chance of recidivism. And so some people felt like some of these features shouldn't be used. They were too unfair to be used. They shouldn't be being put in this classifier. And so prior to this COMPAS system coming out, right, it was judges who got to decide whether or not to admit evidence. So judges could say, hey, this evidence isn't relevant to the facts of the case. I'm not considering it. In the case of COMPAS and a lot of machine learning systems, it's actually the algorithm designer who may or may not have, judicial or subject matter expertise, who's deciding whether or not the features are fair to use. Today, right, we want to try to see if we can take a descriptive approach, which is to say, what if we could follow kind of the public's beliefs about fairness in helping build this classifier? And this is sort of well-grounded, right, in legal literature, where you have a jury of your peers, et cetera, who help make decisions. So maybe the people should be the ones deciding whether features are unfair to use. So we're again going to use some scenario-based surveys. And we're going to describe what happened in Florida. So we're going to say judges in this county in Florida have started using a computer program to help them decide which defendants can be released on bail before trial. The computer program they're using takes into account information about the defendant's stability of employment and living situation. For example, the computer program will take into account the defendant's answer to the following question: how often do you have trouble paying bills? And we varied this for each of the classes of features that were used in the COMPAS questionnaire. We then asked, is it fair to determine if a person can be released on bail using information about their stability of employment and living situation? We pre-tested this survey through what are called cognitive interviews, and we did that on the past one as well, where people kind of think aloud as they answer it, and it helps us make sure that they're answering consistently and they understand the questions. We also used 2 different samples, both crowd workers and the census representative panel like I said before, and findings were consistent. So it's not like the people doing crowd work felt really differently than the rest of the US population. And so what we see is that people have opinions about the fairness of using different features. And this kind of aligns with the outcry, right, that happened after people found out about this. So, using someone's current criminal charges or their own criminal history, people felt was pretty fair to include in the classifier. But using information about like their grade school, attendance record or grades or the quality of their social life or the criminal history of their family and friends, people did not feel like this was very fair to use. And while there were sort of people had preferences about fairness, they didn't like universally agree. It wasn't like everybody was like, no, this feature is not fair and this feature is fair. There was a lot of variance in people's beliefs. And when we have a lot of variance, it's kind of like that security question, right? Like if people's behavior or their preferences aren't consistent or sort of modelable, then it's really hard for us to make inferences or make decisions based on their preferences because we don't know, if they're going to change tomorrow or how they might be applicable to a new situation. So we wanted to see if we could sort of break down people's beliefs about fairness here, just like we did in the case where we figured out that they care about features, and see if we can get to something more well-reasoned. And so what we did was we looked in the literature and we said, okay, how do experts or how do philosophers, how do people in the past make decisions about fairness? And what we found was there were sort of 8 properties that people were using. So they would ask questions like, is this reliable? Is it relevant to the case? Was it obtained in a privacy violating manner? Those are sort of legal questions. Is it volitional? Meaning, do you have control over it? So for example, the criminal history of your family and friends, not really something you have control over. Is it actually like causally related to the thing that we're trying to measure? So maybe like your social life is not causally related. Is it going to cause a vicious cycle or disparity in outcomes, or is it caused by sensitive group membership? Basically, are we discriminating against certain people kind of by group or putting them in a worse position because we're going to use this feature? And so what we wanted to find out was, do these properties help explain people's reasoning about fairness, or are they just sort of making, decisions ad hoc about what is fair? And what we find is that when we go and do surveys to assess people's views on these properties, we're actually able to predict, based on their assessments of, is school history reliable, relevant, private, et cetera, based on that, we're able to predict whether they think it's fair to use that feature in prediction with 88% accuracy. So people are super consistent in their mapping from these properties to fairness. So kind of giving an example, right? If I think this thing is like really reliable, but not that relevant and is too private and is volitional, and someone else feels the same way, we're going to have the same view about whether it's fair. But someone who holds different views about those properties is going to have a different view of fairness. And so the lack of consensus in terms of what features are fair to use was a lack of consensus in these ratings of these properties, not a lack of consensus in like how we map from those properties to fairness. And so what that means is that we kind of need to use a combination of descriptive and normative approaches. So end users are probably not the best people to be evaluating, the properties of these features. Judges or experts are going to be better at saying, is something reliable? Is it relevant? Is it causal, et cetera? But end users can provide the mapping function from those properties to fairness, right? Because otherwise we're taking one judge or one algorithm designer's view. And as we see, depending on, how they evaluate those properties and then how they map, we could get something that doesn't align with sort of the population view. So we can end up using a combination where experts can rate these properties and then users mapping function is used to decide how fair they are. And in the future, we would hope that we might be able to even computationally evaluate some of these properties, right? So people are working on causal modeling. Can we actually computationally figure out whether a feature is related to an outcome, because that information will be more reliable perhaps than one expert or 5 experts' opinions. Okay, so in this case, we were able to kind of ask preferences, and we were able to distill that there is like a well-reasoned or modelable background to why people feel certain things are fair. In order to make decisions, like decide what features to put in an algorithm or decide how to weight those features, we use the same kind of optimization strategy like I described for security, and I've pointed to the paper where we talk about it. Okay, finally, we want to try to get kind of one step further and see if we can make a decision together with the user. So instead of like observing their behavior, inferring things and making decisions, or asking them their preference for fairness and then making a decision, let's see if we can just do it together. And in this example, we're going to be trying to determine guidelines for developing VR content. So we did this a couple of years ago when about 3% of people were using virtual reality. And there are still a lot of questions about, is it okay to have fighting scenarios in VR? Is it okay to have various different kinds of situations, different kinds of biometric data collection, etc.? And what we're going to try to do is co-design a set of ethical standards for VR development with VR developers. And the need for this came out of an interview study that we conducted, where we found that VR developers really wanted these guidelines. So developers were saying things like, there's quite a big list of unknowns right now in terms of what's best etiquette for a user and what's going to keep them safe and comfortable and satisfied. And another developer said, well, it's just the fact of the matter that there are no VR power users or developers. I can count on my hand the number of experienced developers I've actually met. And so in this study, the developers kept asking us as researchers, can you tell me what I should be doing? Can you give me guidelines? And as they were doing that, we thought, well, as opposed to kind of, imposing our expert normative view, let's see if we can kind of create those guidelines together. And so what we did is we started by proposing a set of 6 like high-level principles that we drew from interviews with both VR users and VR developers. And then we invited 11 online communities of VR developers to edit this draft of principles and kind of make it their own. And this is a picture of the document in the midst of being edited. And so as you can see, the developers added this user-centric design and experience principle. They were commenting, they were editing, so on and so forth. And in the week that we did the study, the document got 1,000 views. 245 of those views were people who could edit it, so they were on a platform where they could do editing. Of those, 19 edited and 7 shared. And this engagement is equivalent to what you would see with like Wikipedia editing. And there were 40 unique contributions to the document, so comments, edits, additions, etc. At the end of the week, the developers had reached consensus on 10 principles for ethical development. So we started them with 6, they ended up with 10. And we, did an analysis of their editing process to really understand like how were they getting to consensus. And one of the things that was really interesting was they were sort of building the ethics as they were editing. So one person would say, well, we need to make sure that the technology is accessible to those with disabilities. And someone else would say, well, but what if that ruins the experience? And so someone else can come and say, okay, here's a solution. Let's say you need to make sure that it's modular. So someone could do it, but it doesn't affect the experiments, so on and so forth. So they were kind of building that themselves. And at the end, they ended up with this kind of clean document for ethical development in VR. And subsequently, we saw them building, public open source libraries that address some of these questions, looking for questionnaires, et cetera, and saw this get reshared in those communities, even like months afterward. And that's kind of the power sometimes of doing this descriptive work, is something like co-design, you really get buy-in from the stakeholders. But different sort of descriptive methods are appropriate for different problems, right? So in the case of VR, we are looking for standards for ethical development. And so we've been to the VR developers who are going to use those standards. In the case of like deciding, what features are fair to use in machine learning, we could kind of ask people directly. And then we had to kind of figure out, what was the reasoning behind their decisions, but we could use their preferences to inform us. In the case of security, as I mentioned, users might not be able to express an explicit preference because they may not understand the underlying technology, but by watching their behavior, we can kind of infer their preference. And these methods have prerequisites. So observing behavior or asking questions requires consistency, right? So if people are all over the place, then it's hard to sort of well represent the opinions of the population. So we need to be able to, in the case of fairness, we can predict with 88% accuracy how fair they think it is. In the case of security, at least in a controlled setting, we can model behavior well. We need that kind of consistency. For co-design, because people kind of negotiate, we don't necessarily need that consistency, but we do have to think carefully about who we're involving. So we either need to have a ton of people so that we cover, all the possible sets of experiences and views, or we need to kind of pick participants or communities of participants who seem well-intentioned, right? There's always a concern in co-design kind of things that we could have malice. And I bring up this example because sometimes people ask me, well, why didn't you have VR users do co-design? And one of the reasons for that is that as researchers, we made a normative decision to only work with developers at the beginning, because when we had done our interviews with VR users, there were not a lot of VR users, right? 3% adoption. And they were extremely homogenous. And they were kind of exclusionary as well. So they said, if you use VR, most likely you also use Reddit, because there's a certain type of crowd that's really into this. Someone with a lot of money, who has a premium setup. You're talking people with 4+ VR sensors. And someone else said, I'll be more concerned about virtual crimes or bullying when VR becomes more accessible to the general public. And those were 3 different participants, and we heard this kind of over and over again. They were like, well, our guidelines for VR development is make the barrier to entry high, don't let people in, that will keep me safe, I will be happy. And that's not necessarily what we thought was sort of the right approach for doing this co-design, at least for starting it. So descriptive to normative solutions, it's always a balance. So like I said, in security, we have normative sort of expert judgment on what behaviors are most effective. Is it that experts are necessarily the best for setting norms? I mean, maybe we can have computation systems do it. Sometimes that can be even more kind of effective or give us better ground truth. So can we compute the effectiveness of security behaviors and bake that in with our models of how people are going to behave? In the case of machine learning, right, we need experts or computation to compute these property values like reliability, causality, et cetera. And then we use the public's preferences to map that onto fairness. And in the case of VR, right, as researchers, we made a normative judgment about who to include in this co-design in order to kind of keep with the intent of growing VR. And so you can kind of endlessly have these descriptive normative decisions, right? Who decides where on the balance point we're going to fall? Is that a descriptive decision or a normative decision? So on and so forth. So in today's talk, we explored how descriptive solutions can help us solve computational problems. So ways that we can listen from and learn from people in order to infer best practices. We talked about some examples in security, machine learning, and VR, and illustrated how we want to achieve different balances between normative and descriptive approaches, depending on the particular problem. Thank you, and I'm happy to take questions now.